Limitations of CFT. See, CFT have been very successfully able to explain the formation, color, magnetic behavior, and even it was the first theory who has actually quantitatively has given us the data to arrange the ligands on the basis of the crystal field splitting energies, but it has certain limitations also. First, it regards the nature of bonding between the ligand and the metal ion as completely ionic. But what about the covalent? Because if it is ionic, all the ion must split up the moment we put them in water, but the coordination entity always remains intact. So that's the first weakness of this limitation of this theory. The second, the most important, if there is a splitting, the splitting is caused due to the coming ligand. Definitely anionic ligands must cause maximum repulsions, but all chloride, fluoride, iodide were found to be having the least value of the crystal field splitting energy. This is how. There is no explanation to this. So that is how. These are the few points which were not explained clearly by the crystal field theory, and that is why we have switched to the more advanced theories like ligand field theory and MOT, molecular orbital theories. But that are beyond the scope of this textbook and class 12. This will be done later on if you are doing pure chemistry in a higher level. Bonding in metal carbonyls. See, carbon monoxide forms mainly homoleptic complexes or coordination entities with the transition elements. Now, these coordination entities are of different structures. Like I can give you an example. We can have carbon monoxide with nickel. It's called tetracarbonyl nickel, which is actually is tetrahedral in shape. Similarly, we have pentacarbonyl iron 0, which is actually trigonal bipyramidal in shape. Similarly, we have hexacarbonyl chromium 0, which is octahedral in structure. With manganese, it forms this kind of a complex, which is called decacarbonyl dimanganese. In this case, both the manganese atoms are bonded to each other through a single bond, and both of these are having square pyramidal structures. Similarly, with cobalt, which is 27 atomic number, it forms this kind of a complex, which is called octacarbonyl dicobalt, in which both of these cobalt are bonded to each other through a single bond, and both are having the square planar structures. So these are the different structures in which these metal carbonyls exist. But what is most interesting to note about these metal carbonyls is, remember that carbon monoxide is a weak Lewis base because it is having a resonance, due to which the lone pair present on the carbon is involved. It's not readily available. But in spite of being a weak Lewis base, it's a very strong ligand. It forms a very strong complex. The reason being why it forms very strong complexes or coordination entities, the reason is because of its tendency to form what? D pi p pi star back bonding. Now, due to this d pi p pi star back bonding, its bonding with the metal ion becomes very, very stable. Let me explain to you. Like if suppose this is the metal with the empty d orbital, and this is what you are having, your carbon monoxide, which is actually through its orbital, which is having a lone pair, it is giving this, donating the lone pair to the metal ion and forming a normal sigma bond.